Trains are interesting. There is lots of friction between the engine wheels and the track, so the engine wheels won't slip. But there is almost no friction between the train car wheels and the track, so the train won't lose speed unless the brakes are applied. Let's draw free body diagrams for each car and the engine below, and calculate the size of each force using Newton's first or second law as appropriate. The two cars are each 120 kilograms. The engine is 300 kilograms. The train is accelerating to the right at positive 2 meters per second each second. Let's call the tension between the last two cars tension 1 and the tension between the first car and the engine tension 2. The engine is using friction to pull the whole train forward. We can start with three free body diagrams, one for each car and one for the engine. The vertical pictures are not very interesting. They all have a balanced weight and a normal force. They each have a balanced weight and normal force. The last car has a tension 1 pulling it forward. The middle car has tension 1 pulling it backward. This is the third law partner to the tension on the last car. The middle car has tension 2 pulling it forward, and tension 2 must be winning, so I will draw it longer. The engine has tension 2 pulling it backwards, and it has friction pulling it forward. The friction must be winning because the train is accelerating to the right. Let's start the math at the back of the train and work our way forward. The first law applies in the y direction. The weight is equal to the normal force. They are both 1,200 newtons. The second law applies in the x direction. Tension 1 is the force responsible for pulling the mass of the last car forward. The sum of the forces equals ma. Tension 1 equals 120 kilograms times 2 meters per second each second. This means that the tension is 240 newtons. The middle car is also in equilibrium in the y direction. The weight is balanced by the normal force. They are both 1,200 newtons. In the x direction, we need to use the second law. Tension 2 is pulling forward against tension 1, which is pulling the car backwards. The sum of the forces equals ma. Tension 2 minus tension 1 equals ma. The first tension was 240 newtons, so tension 2 minus 240 newtons equals the mass of 120 kilograms times the acceleration of 2 meters per second each second. That means tension 2 must be 480 newtons. Now we come to the engine. Once again, the forces are balanced in the y direction. The weight is balanced by the normal force. They would each be 3,000 newtons. In the x direction, we need the second law. The engine is using friction to pull the train forward. The friction minus tension 2 is equal to ma. The friction minus 480 newtons equals 300 kilograms times 2 meters per second each second. That gives us a friction of 1,080 newtons. And we're done. We solved this problem by applying the second law 3 times, once to each part of the train. As a check, we could solve this differently, by applying the second law once to the whole train. The engine is using friction to pull the whole train forward. So I can start with the second law. The sum of the forces equals ma. Friction equals the total mass, 120 kilograms plus 120 kilograms plus 300 kilograms times the acceleration of 2 meters per second each second. So the friction equals 540 kilograms times 2 meters per second each second. Notice that this also gives us a friction of 1,080 newtons. We get the same answer. That's good. When using Newton's laws on complicated systems, you can apply the rules to the whole system or to any part of the system, and you'll get consistent answers. Here's a situation that is similar to the setup of the friction lab we did. There's a coefficient of friction of 0.1 between the big box and the table. The big box accelerates to the right at 0.5 meters per second each second. Use free body diagrams for the two boxes and Newton's first or second laws as appropriate to find the tension in the string and the mass of the hanging box. There are 2 things to solve for, and we will get our answers from the 2 free body diagrams we draw. The block on the table is experiencing 4 forces. There's a weight, a normal force, some friction, and some tension. The problem is suggesting that the block is in equilibrium in the y direction, but it is explicitly stating that the block is accelerating forward. The hanging block is experiencing 2 forces, weight and tension. If the green block is accelerating forward, that implies that the red block must be accelerating down. Like the train problem we just did, if these blocks are connected, they must be moving together. The vertical problem for the green block is easy. We write the first law and we state that the normal force is balanced by the weight. Both forces are 100 newtons. In the x direction, we start with the second law. The tension minus the friction equals the mass times the acceleration. I can replace the force of friction with the coefficient of friction times the normal force. I have values for mu and the mass of the green block and the acceleration. This allows me to calculate the tension, which is 15 newtons. I have one more problem to go, the vertical problem for the red block. The red block is accelerating down, so we'll use the second law. The weight minus the tension equals the mass times the acceleration. I can replace the weight of the block with gm. G is 10 newtons per kilogram, and I don't know m. I do know the tension and the acceleration. If I simplify my math and combine like terms, I get 9.5 times the mass equals 15, which means that the mass is 16. The red block has a mass of 16 kilograms. For our last example, I want to talk about elevators. Draw 4 free body diagrams for this person that's standing on a bathroom scale in an elevator. The motion in each situation is different. For each one, also write a specific equation for the sum of the forces in the y direction using formal force symbols. When the elevator is not moving, our passenger is in equilibrium. There is a balanced weight and a neural force. This is a first law situation. Weight is equal to the neural force. When the elevator is accelerating up, there's a small change to the free body diagram. This is now a second law situation, and the upward force must be winning. The Earth is not pulling down on the guy less, so the neural force must be bigger. He would feel heavier, even though he is not actually heavier. When the elevator is accelerating down, the neural force is smaller than the weight. He would feel lighter, even though he is not actually lighter. If the elevator is moving at a constant speed, the weight and the neural force are balanced and the guy is in equilibrium. It does not matter whether his constant speed is upward or downward. Let's suppose that the mass of this guy is 65 kilograms. At a particular moment, he looks down at the scale and it says 900 newtons. What is the acceleration of the elevator at that moment? We can start with a free body diagram. We know that the neural force is 900 newtons. That's what the scale says. A 65 kilogram guy is supposed to weigh 650 newtons. This means that the upward force is winning and he must be accelerating upward. The sum of the forces equals the mass times the acceleration. The neural force minus the weight is the mass times the acceleration. 900 newtons minus 650 newtons equals 65 kilograms times the acceleration, which leaves me with 250 newtons equals 65 times the acceleration, and that gives me an acceleration of 3.8 meters per second each second upward, because up was winning. Here's an interesting thought experiment. Let's suppose the elevator is at the top floor, but at rest. We ask the guy to hold out a rubber ball at shoulder height and release the ball on the count of 3. But when we get to 3, we cut the cable holding up the elevator. What does the guy observe the ball do? What does the scale say at that moment? Use free body diagrams to help answer these questions. Before we cut the cable, the guy is in equilibrium. His weight is balanced by the neural force from the scale. When we cut the cable, his free body diagram changes. The Earth is still pulling him down, but the floor is no longer holding him up. When we cut the cable, the elevator starts to fall. So does the scale, so does the guy, so does the ball. Gravity is pulling them all down at 10 meters per second each second. Since they're all falling at the same rate, there's no relative motion between them, and the guy thinks that the ball and he himself are floating. He feels weightless. But he's not weightless. He's about to die because his weight is causing him to plummet to the ground. We'll talk about this more in class.